Welcome to next session on the book Elements of Programming. Before starting chapter 2, we will go over the summary of chapter 1. So we skipped section 1.1 to 1.3 and we covered procedures and specified that a procedure have input and output, and there are three types of state associated with the procedure. One is local state, one is global state, and one is the procedure's own state. Local state is the set of variables which like set of objects which are created when the function is executed and are destroyed when the function is returned. Global state is something that is shared across all the functions and anyone can modify the global state. And on by on state we saw an example of static variable that was local to the function itself. Next we covered regular types, and regular types are those types that behave similarly to the integer types. Now, we saw that regular types have some properties. One is related to lifetime, where we specify default constructor, copy constructor, and destructor. Next, we have one assignment. Then we had equality and total ordering. Basically, it follows the trichotomy law of real numbers, where given any two elements, either they are equal, or first is less than second, or second is less than first. Then we had underlying type, but we skipped that because we will cover it in later chapters. Next, we covered the concept of well and partially formed object, where if an object is well formed, it means that we can apply any operations like assignment, equality, copy constructor to it. But if an object is partially formed, we can only apply two operations. One, we can destroy it. Second, we can assign new value to that object. So basically, we saw two examples. One is intx and one is string of s1. In case of intx, we are using default constructor, and also in case of string of s1, we are using default constructor. X, if it was integer, we know that it is not initialized, so it contains garbage value, and accessing it is undefined behavior in C++. So we can only do destructor and assignment to it. But for the case of s1, we know that s1 is initialized as an empty string. So s1 is partially as well as well-formed object, whereas integer x is only partially formed object. It is not a well-formed object. Okay. Next, we covered the concept of regular procedures, where we say it is just like pure functions. It means that if we call this function and again, we always get the same result, and implementation of this function has no impact on how we use it. So basically, we have well-defined interface for the function, and implementation is up to us how we are going to implement it. But as far as implementation is concerned, we don't care how it is implemented. Next, we cover concepts, where we specified that concepts are basically predicates of the types where the predicates are evaluated at compile time. Okay, now let's come to chapter 2. So in chapter 2 of elements of programming, we will cover transformations and their orbits. And what are those? We will see. So coming to section 2.1, we first cover transformations and basically definitions related to it. So what is a predicate? We covered this in previous session as well. Predicate is something whose output is boolean, nothing else. Boolean value. By boolean value we mean true or false. Okay. Next we covered partial and total functions. So earlier you remember that we had the concept of domain and definition space, where by diagram we saw that, let's say this is a domain, then we can divide this domain into two parts. Domain of a function. One part where the function is defined. We if we, let's say, take an element x from this section of the domain, the function will always terminate and will always give valid value. But if we take, let's say, y point from other part of this domain, the function may or may not terminate. It is unspecified. Basically, calling the function on that variable y is undefined, and we should not call that function in the y. Okay, so if definition space is exactly equal to domain, we say that function is total function. If definition space is subset of domain, we say it is partial. Simple. By total, we means everything is included in the domain. We can call this function with totally any value. But the function is partial if instead of every element in the domain, we can call it only for a specific subset of elements in the domain. Okay. And in the book, we also have the concept of non-total function. You are encouraged to also go through the definition of it and how these three things are related. Okay. Coming to definition space predicate. So if this is the domain of function, the definition space predicate, let's say it is denoted by a function p, it takes x and it will return true if fx is defined or x is in the definition space of f. Okay. Otherwise it is false. So basically, if definition space predicate gives us true, it means we can freely call that function on the given particular value. If definition space predicate gives us the value false, and why definition space predicate? Predicate means true or false. By definition space, we mean this predicate will give true or false based upon whether the given input is in the definition space or not. Okay. So let's take an example of sum of two integers. We have one function. Let's say I am using 32-bit 2's complement integer, and I have int sum, int a comma int b, and I am returning a plus b. Okay. So what is the domain of this function? The domain is int percent. As per definition, as per the definition of the book, since this is a homogeneous function, the domain is also single int. But from mathematical point of view, we are going to treat it as domain of integer cross integers. Okay. Now, what is definition space predicate? Definition space of this function. Is it int cross int? Like, is it domain? The answer will be no. Why? Because if I call sum with int 30 of max and int 32 of max, the result will be overflowed integer, and the result can't be represented in the output type of int. So there are some pair of inputs for which this function is not defined. Okay. So how do we write the definition space predicate of this function? So let's say we have boolean and this is some predicate which takes same arguments as the original function. Now, how should we proceed to write this some predicate? We know that some predicate is well defined if the output is also a 32-bit and 32-bit signed integers. So minus 2 to the power 31 is less than equal to a plus b is less than equal to 2 to the raised to power 31 minus 1. Okay. Now we have two cases. Case number 1, b is less than 0, and case number 2, b is greater than 0. And based on these less than and greater than sign, we can simply write, okay, if b is less than 0, then a should be in this range. If b is greater than 0, then a should be in this range. Otherwise, we return true because the sum is going to be anyway a, and a is already representable in the input type. Okay. And coming to our fourth concept, which is a transformation. So transformation is simply a function from type t to t where, like, just transformation is simply a unary function from which takes an input of type t and it returns an output of same type, nothing else. Okay. So now let's go into the powers of the transformation. First, we see, let's say we have input x and we are assuming, let's say, function is defined on every value of x for our discussion for now. So we have f of x, which is a function from type t to t. Okay. So let's say this is set of all possible values of type t. This is our x. If I apply function f, it is possible that this goes to another value y, where y equal to f of x. Now, since y is also of type t, I can reapply the function f on y again to get z, where z equal to f of y, or we can write f of x. In simple terms or in short notation, we can write it f of 2x, where this 2 means applied twice. Okay. For example, let's say my function fx is x plus 1. Now, for f of 0, I have 1, f of 1 equal to 2, f of 2 equal to 3, and f of 3 equal to 4. Alternatively, I can say that f of 0 equal to 4. Or in short notation, I can say f applied 4 times on 0 gives 4. Okay. F can be any function from same type to same type, like from type T to same type. Now, how do we like can we define the powers recursively? And the answer is yes. So if I apply function once on x, I get a new value. If I apply a function twice on x, I get another value. If I apply a function thrice on x, I get another value. So let's denote as a base case, f applied 0 times on x gives x. This is our base case, and it fits very naturally into our definition. How? Let's see. So fx is fx. F of 2 of x is simply f applied on fx. F of 3 of x is simply f applied on f2 of x, right? So we can say that f of nx is given by x if n is equal to 0, and f of fn minus 1x if n is greater than 0. This is our definition. Nothing new here, right? Okay. So we covered powers. Now let's see how the powers are related to integers. Again, we are going into discussion of the structure that is represented by powers of function. So let's say this is the set of integers, right? And in earlier sessions, we started integers with 1. 1 is not any particular value. We could start it with 0. So for our discussion, we are going to start integers from 0. So what was the structure of integers? We have starting element, and from starting element, we are able to generate more elements, which goes up to infinity, where first element represents 0, 1, 2, 3, 4, 5, and so on and so forth, right? Next, we have powers of function, where initial element is, let's say, x. And if I apply f on it, I get f of x. If I apply f on it again, I get f2 of x. If I apply f again, I get f3 of x, and so on and so forth. So we can see that computing nth power is basically equivalent to the structure that is posed by integers. So basically, let's say we want to compute f of 10 of x. To compute f of 10 of x, we can't do anything other than going one by one, right? Although there is some algorithm known as binary exponentiation, we are going to cover it in later chapters. But for now, since our structure is very basic, we if we have to compute f of n of x, we will compute it by a repeated application of function f, simply up to n times. And this is the algorithm given in the book. So what are the pieces here? First, this specifies the types. So these two are the types. They can be arbitrary types. Next, this is the concept. This is the function name. This is the type, and this is the variable. Again, n is the type, small n is the variable, and capital F is a type, small f is the variable. And return type is domain of f. It means it is codomain of same f function. Okay. So what is domain of power unary? It is equal to cross product of domain of f n and f, where n is the integer and f is a transformation. Okay. So it is specified here that f is a transformation and n is the integer. And what is the type of x? Since f is a transformation, we know that f goes from type t to t. And by writing the type of x as domain of f, we simply say that t equal to domain of f. So basically, type of x belongs to domain of f. Okay, so we have only two degrees of freedom. I mean, we only have two distinct types, and the type of x is derivable, or we can reduce the type of x from these two types. Although in this case, we only use the type of transformation. But you get the idea, right? So this was the definition, and the things can be checked at compile time. This requires clause which can be checked very easily at compile time. Compile time check. Now to compute the nth power of f, we have one precondition. This precondition specifies the definition space. Okay. So what is the precondition? Precondition says that n is greater than equal to 0. Very good, because we only defined f the power of function on 0th power, first power, to second power, and so on and so forth. Right? So n should be greater than equal to 0. It should not be the case that n is less than 0. Although yes, we are referring to integers, and by integers we also have the -1, -2, -3, and so on and so forth. And we are only considering about natural numbers here. That's why we have written n greater than equal to 0. Second condition, okay, and this symbol means and, if you were not aware. And we have third symbol that for all I in the n. What is n? N is not a natural number here. N is the input type of integer. So for I equal to 1, 2, 3 up to n, f of 1 of x is defined, f of 2x is defined, and f of n x is defined. We are assuming this. We don't have any definition space predicate. We are assuming implicitly that these things are defined. Okay. So now we clarified our definition space predicate, or like definition space. Now let's come to implementation. Again, let's see how fn of x was defined. Fn of x was x for n equal to 0, and f of n minus 1x for n greater than 0, right? So we could write it in two ways. One is recursive and one is iterative. In recursive approach, the implementation will be very simple. So this is the function name and these were the input arguments. And we have if n equal to 0, then I simply return x. Otherwise, I simply return f of function applied again with n minus 1. Simple. But the author of the book has decided to go with iterative implementation because iterative implementation is very easy for from implementation perspective, also from the, like, not easy, but it is very performant. We don't have to create a very long chain of call stack and come back, collapse the call stack and all those things. So what is this algorithm doing? It is very trivial algorithm. I believe I shouldn't have to explain what the algorithm is doing, but you get the idea. How domain is defined, what is the definition space for this function, and how that this type is derived from types n and f, right? So the idea of this algorithm is that the implementation is very much generic, and by generic implementation we can use this algorithm to compute nth power as long as we have such type of structure. For instance, let's say we have pseudo random number generator, where with pseudo random number generator we know that we have a seed value, and by first iteration we get another random number, on second iteration we get another random number, on third iteration we get another random number, and so on and so forth, and it is deterministic. So if, let's say, for a given seed we wanted to compute 100th random number in this sequence, instead of writing this thing again and again, we could use this implementation, existing implementation. How? We could say power unary with, let's say, seed was 100 or 101. Next is the how many times we want to compute. We want to compute it 100 times. And what is the function? Function is simply a lambda, which was basically takes an input x and gives next random number based on x. So to compute 100th random number based on the given seed of, let's say, 101. Instead of writing for loop again and again, we could directly use this implementation. Okay, let me clear this. I meant to write x goes to next random number based upon x. And this is a function which takes an input of type t and returns a type t, because this is one input and the output will be some value of type t, where t is the integer here. Okay, now coming to section 2.2, where we have defined orbits. So till now we have defined transformation. Now we expand our view on the global behavior of the transformation. So what is reachability? Again, so we saw that transformation just follow the structure like integer, and there are no, now this is new information. So let's say this is the input element, starting element. By applying function we got new element, by applying function again we got new element, by applying function again we got new element, and by applying function again, let's say we reached the starting point again. Is it possible for any transformation to have such property? Definitely. We didn't have any such restrictions. We only meant that f of 0 of x equal to x, f of 1 of x is x applied, f applied once on the x, and f of 2 of x is applied, f applied twice on x, and so on and so forth. There was no restriction on that the elements should not be repeatable. Okay, so one particular example of cyclic function will be f of x equal to x plus 1 for x, let's say, unsigned 8-bit integers, where we know that adding 1 to 255 will give us 0. So if our starting element was 0, applying function we get 1, applying function we get 2, applying function we get 3, applying this function again we get 255, and applying this function again we get 0. We have not went into undefined behavior. Every value is in the domain, like definition space equal to domain for this function. So now that we have this in mind, what is the reachability? Reachability is something that, let's say we have two nodes. This is node x and this is node y, and we didn't have any cycle for the sake of simplicity for now. And this list goes up to so on and so forth. Okay, so x is reachable from y if, after applying n greater than equal to 0 transformations on y, we can reach x. Very trivial definition, nothing new, nothing fancy here. So we say that x is reachable from y if, by starting from y, we can reach x by applying function again and again, at least, maybe not applying it at least once as well, because if x is equal to y is allowed as per this definition, we have to apply the function 0 times, so that this relation reachability is a reflexive relation as well. Okay, next, coming to cyclic structure, which I already covered. A transformation generates a cyclic structure if, after, let's say, n greater than equal to 1 applications of function, I get x equal to f n of x. Like after applying n transformation on the starting element, I get x again. If this is the possibility, then I say that my transformation is cyclic. Nothing new. Next comes the concept of terminal element. Now, let's say our function was not total function. It means there are some values where the function was not defined. So let's say we had some starting element x, we went into f of x, we went into f applied twice on x, and so on and so forth. And after reaching mth index, we are not able to apply f again. You might ask, what would be an example of this type of function? This function can be fx equal to x squared for x belong to int 32 types. Why? Because after applying f on 1, we get 2, then 4, then 8, then 16, then 32, up to. After applying this function, I believe, how many times? N times. not not this chain. We will get 4, 16 to 56 and so on and so forth. After let's say 8 or 10, I believe 10 steps, we will reach a point where successively applying this function is not defined. We will overflow, right? So we have example of such function. So terminal element is basically the last element after which we can't apply the function. Simple. Next comes the orbit. Orbit is nothing but basically set of all the possible values that are reachable from given starting element. Okay, nothing new here. Then comes the concept of distance. Distance is basically how many times I have to apply function f to reach from x to y. And we are assuming that distance is directional here. It means that distance of x comma y is not necessarily equal to distance of y comma x. Okay. So in above example, let's say we could apply function f at most m times. So we could say that distance between these two elements, distance of x comma f applied twice on x is equal to 2. But distance on between these two is undefined. Why? Because in this structure we can't move from f applied twice on x to x. There is no way to go there. So we have to keep this in mind. Coming to our next slide. Yeah, so we have distance algorithm where we say that we are taking a transformation of f, like f, which is a transformation here, and we are taking two elements. One is from the domain of f, and second is also from the domain of f. And we want to compute distance between x and y. So it is a precondition that y is reachable from x under transformation f. Otherwise, distance have no meaning, right? So, and you can refer to the book y distance type of f or how it is defined. Now, if x was equal to y, this algorithm will simply return 0. And if x is not equal to y, since we are assuming that y is reachable from x, eventually, after successive application of f on x, we will reach the y. This algorithm is trivial. I don't believe I have to explain anything much here. Now, coming to last point of today's session, how many types of orbits can we get? So earlier we saw that a transformation can go up to infinity, just like if we move outside our computer science perspective, or like types in computer science, or like types in our programming languages, built-in types. We study integers, then we see that our transformation can go up to infinity, where f of x is simply defined by x plus 1 for natural numbers. One case is this. Second case, we saw an example of terminating sequence, where our f of x was x square. So we saw where we have the starting element and eventually we reach an element from where we can't move any further. This was second case. Third case, where we had f of x equal to x plus 1 under 8-bit unsigned integer. We saw that after we reach final element, we were able to get back to the first element. There is one more case, and that structure is like this. Let's say we applied this function sometimes and we get back to the middle element. Okay, so this is like a partial cycle, not partial cycle, like we have one complete cycle and we have some structures like some linear sequence of elements before cycle is started. So we have these four types of possible values that our function can take. Okay, one is infinite, one is terminating, one is circular, and one is row shaped, where this portion represents the handle and this portion represents the cycle. That's why row shaped or p shaped. Okay, now coming to various terminologies related to it, these are very simple terminologies. One is finite. So these three cases are finite and this is infinite orbit. right? And I believe I don't have to explain why these are finite and infinite, so we can move forward. Next, we have cycle. So this is the case for cycle. We have handle, and in this case we also have this as cycle. This is cycle and this is cycle. The initial part is known as handle. In case of handle and cycle structure, the common node, this one where handle and cycle meet, is known as a connection point. Okay, and in an orbit, my handle size, orbit size, and cycle size. So let's say orbit size is O, handle size is H, and cycle size is C. In this particular example, handle size is 2, H is equal to 2. And let's say we only had 4 elements in the circle, so in the cycle, so we had cycle size equal to 4. And orbit size is basically number of nodes in the structure. So for this case, we have 6 nodes in the structure. We can say O equal to H plus C. Okay, nothing new, nothing fancy. All these things are trivial. In the next session, we will cover the algorithm of collision point, where we will see that for given arbitrary structure among these 3 types, because we will assume we are not dealing with infinite case, what is our structure, how many elements are present before the cycle, how many elements are present in the cycle, and which nth value will give us the connection point. Like if we have a starting point x, which value of n, or basically what is the handle size, after application of handle size, what will be the value that we will achieve. So our target will be to determine 3 things. One is the handle size, one is cycle size, and this connection point, the value of this connection point. Okay, see you in the next session.